Hello and welcome to another Crafting Interpreters video. In this series, we are going to read the book Crafting Interpreters by Robert Nystrom and implement an interpreter for the programming language logs using Go. In the previous video, we implemented an AST debugger class, or more precisely, an AstPrinter struct, and this struct uses the visitor design pattern from the Gang of Four book to implement polymorphism. And if you have watched the previous video, you may remember me struggling a lot with Go's approach to generics, but luckily we have done it correctly, and now this compiles. So in this video, we are going to follow on this topic. And if you are new to this series, you can watch the you can read the whole Crafting Interpreters book for free at craftinginterpreters.com, and you can get the source code from the previous videos from a link in the description below. And now let's see what the book has in store for us. Okay, so this snippet of code implements a parenthesize method, and we've already implemented that one in here. And we even got a nice equivalent of the string builder. There is actually a string builder class in Go, except that it's not a class. And yes, back to the book. It takes a name and a list of sub-expressions and wraps them all up in parentheses, yielding a string like this. Note that it calls accept on each sub-expression and passes in itself. This is the recursive step that lets us print an entire tree. Side note, this recursion is also why people think the visitor pattern itself has to do with trees. We don't have a parser yet, so it's hard to see this in action. For now, we'll hack together a little main method that manually instantiates a tree and prints it. Okay, let's see. Wait. Oh, no. Okay, so in order to implement a hackish new thing. Okay, so this basically asks me to implement a new package, and this means that at this point I probably have to start implementing things in separate packages. And this means I'm going to need an expression package, I guess, and okay, let's see what we can get here. So I'm going to spend some time moving things from the main package to the expression package, and let's see if we can get some meaningful results from that. We'll probably bump into some sort of circular dependencies at some point. Okay, so these types, I think this file is kind of self-contained, which is good, except that we're also going to need a token package, I guess. So token type goes here, and token type like this. This goes here. Okay, this is self-contained, which is nice. Then we are also going to need this, and this goes away. So this goes away, and then token itself, I think this can also go to the token package, except that in the token token.go we get this, package token. Okay, and this seems correct. And now it's going to complain that the it's because the token type does not currently implement the stringer protocol, the stringer interface. So we need to run go generate, I think. Did it work? No, it did not, obviously. Go generate, like so. And now we should, yeah, now we also got this file generated inside. So the difference is that when I tried to run go generate without any arguments, it only ran in the main package. And if I run it like this, it recursively runs it in all subdirectories, which is what we wanted. Okay. And now the AstPrinter thing. Okay, first we can get rid of this file and then these errors. Okay, I don't think we will need them outside of this this package for now, maybe. Or maybe, you know, what's in scanner? Okay, so now this is going to need token, like this. No, not this one. Token, import, github.com, moros, go logs, token, like so. Okay. And this means that for here, we're going to need token this. Okay, so I can already see we're going to get a lot of things. Okay, can we do a full import? I think I remember there was a way to import everything in a Go import thing. Can you get something like go.doc import? Nope. I think there was like a full total import thing. Okay, then if not, we're going to need to basically prefix everything. So I guess we can just use some Vim magic. Token type, we replace it with token type. GC, not this one, not this one, this one, this one, this one, this one, this one. Yep. Yes. Yes. This is token type. And I think the mapping of keywords, this could actually belong, you know, this could actually belong in the same package, I guess. Or maybe it could just go to a scanner package or something. Like so. So if this goes into the scanner package, then and now it's going to need the errors. So the errors could all go inside. I think this whole package could just go to scanner. And yes, scanner. And wait, what? Yes, this is correct. And now, okay, let's see if it still complains. So I think in token type, we could actually move this thing to this scanner thing. And then the import github.com moros go logs token. And then we do the same thing, except that now we don't need to confirm. And now can we compile? Undefined expression. Okay. So maybe this AstPrinter could go to the expr part or something. And AstPrinter could go to expr. Okay, can you compile now? Undefined new scanner. So now we can say this is scanner. And now we cannot call scan tokens like this because this is private, so we have to rename it. Nope. Okay, why can't we rename it? Main. And now we have to publish tokens like so. And now we're going to get a whole lot of new errors. S.tokens undefined scanner.go. So scanner 31 s.tokens equals s.tokens. And now we should have two fewer. Okay, undefined VM. So this means that the scanner is actually going to need a pointer to the global state. I don't think we can avoid it anymore, right? So VM will have a pointer to, and now we cannot really have a pointer to the log string because okay, I'm going to call it logs for now, and maybe this will come biting us at a later point, but for now I'm going to put this logs thing inside here, and I'll make it a package variable for now, and run is undefined, and okay. So now this is going to be okay. Okay, so I'm going to put it here. I'm going to make it local. And this has to go here. And this also means that if we make it, okay, now we're going to get a circular dependency, because if we need the scanner in here, oh boy, if we need scanner inside of logs, then we cannot use logs inside of scanner. So we could make okay, so, and this okay, but I think the only thing we are actually going to need the VM inside of scanner is report error, report error, report error, report error. Okay, so I think we can just define it like so. Type VM interface, and it's going to have report error line int error, like so, and then the VM in here. So now we give it like this VM thing. So now we pass ourselves and this thing like this. So now can you compile at least? Undefined token. Okay. So VM reporter is undefined. This means that in scanner, wherever we use vm.report error, we have to get a reference to like we need to do it with the receiver. So, and now s.vm, and this is a public method. And now we are only left with 5 more errors. In scanner.go, we need like s.tokens undefined, s.tokens. Okay, this is public, and 158. This is token, and then 201 token type string, and 238 is okay. So now does it run? It still seems to run in the same way as before. So we did a very short, like a very brief rearrangement to actually move things to their own packages. And I'm not exactly sure if this is not going to come and bite us in surprising ways. I think it will. But for now, until that day comes, and someday, and this day may never come, this is going to bite us. But until then, let's enjoy it. Also, this was a Goldfather quote. So I'm going to commit, rearrange packages. Okay, good. So now, I think what they wanted to tell us was that we can experiment with AstPrinter. So I'm going to create a new file in here with the specific intent of testing the AST thing. So we're not really testing, we are just trying it out. Okay, expression equals expr dot binary, and do we have a constructor? We do. And no. So, but can we construct it like this? Oh shit, we have to define. Okay, I think we can do it with any for now. And yeah, and on the left we get expression unary, and this is going to be any for now. Cannot use expression unary as expression any. Missing method except. Why? Wait, what? Missing method except. Did we actually did we not? Wait, what? Okay, so it seems that we have not expression unary string does not implement expression except wait. So does unary accept anything? Oh yeah. But what does actually implement? So are we trying to say we need to implement accept for everything or what? Hang on, I need to know if we actually need to. Okay, I think we do have to generate and accept. Okay, yes, so I think we do need to implement this acceptor thing for, okay, so for what, for expression func a unary of R accept and this is a visitor of R and this returns R, return E accept a visitor visit unary expression with this, right? And okay, and now what? Undefined token. So this is token.token. This is token.token. Okay. So now operator lexeme undefined. Type token has no field or method lexeme. So doesn't it? Wait, token. It does have. Okay, so this is not this is in the incorrect token. So import github.com/moros go logs token. Right. So what can we what do we get now in the AstPrinter thing? So we can use unary. Great. We can use unary as an expression because we did implement a visitor thing. And now I'm going to move it to the right side of the screen. Unary, we have inside we have a token. Operator is a token, new token, and token type minus with a minus string. Now what is here? Literal nil and line 1. Great. And then in the on the right side we have an expression literal, and what do we have here? with a value of 1, 2, 3. And now we also need to say can't use generic type without instantiation. So like so. Okay, so now it says cannot use expression literal as expression value in struct literal. Expression literal of string does not implement the expression missing method accept. So this means we have to go back to expression and implement the visitor thing. So literal of R, accept visitor of R, visit literal expression E. So now if you go back, the type contract is satisfied, and this is so complicated, like seriously. Anyway, I don't think I'm going to be using I don't think I'm going to be using generics anytime soon to this extent. Or I mean, I don't think I'm going to be using the visitor pattern to this extent anytime soon. Okay, operator is token, new token with token type star and nil and 1, and then we get the right side is a grouping expression with the literal, wait, what? And what does the grouping expression contain? Okay, we need to pass this. An expression is expression literal of types literal of string with a value of 4568, like so. And now it says we cannot use expression grouping, and this means we need to implement the acceptor for the grouping expression. So a grouping, we visit grouping expression with itself. So now it does seem like the type errors are gone. So now I can say fmt println ast expression AstPrinter and now we are probably also cannot really in the AstPrinter we probably need to define this print thing. Okay, now it's public already. So why can't we use it in here? Printer equals this and printer print expression. Does it work like what now? Can it use expression? Expression binary does not implement this, so we need to implement acceptor for the binary expression. Okay, so in expr, yeah, this is a lot of boilerplate. Binary expression E. Okay, now and what now? Can we go to exp run like so? Okay, I guess it did work just fine. So I'm going to commit AstPrinter. Okay, great. So this was very complicated indeed. What else does the book say? You can go ahead and delete this method. We won't need it. Also, as we add new syntax tree types, I won't bother showing the necessary visit methods for them in AstPrinter. If you want to, and you want the Java compiler to not yell at you, go ahead and add them yourself. It will come in handy in the next chapter when we start parsing logs code into syntax trees. Or if you don't care to maintain AstPrinter, feel free to delete it. We won't need it again. Earlier I said that the pipe, star, and plus forms we added to our grammar meta syntax were just syntactic sugar. Take this grammar. So this expression Okay, also I'm starting to become very much afraid that this expression thing is not going to function very well. Or maybe we could do something like this. Oh yeah, I don't know. I feel like this can be complex. Produce a grammar that matches the same language but does not use any of that notational sugar. Okay, I don't think I care too much about the formal syntax for the grammar. What kind of expression does this bit of grammar encode? This is obviously I think it's a function call thing. Or is it? No, I don't know. I'm not sure. The visitor pattern lets you emulate the functional style in an object-oriented language. Devise a complementary pattern for a functional language. It should let you bundle all the operations on one type together and let you define new types easily. SML or Haskell would be ideal for this exercise, but Scheme or another Lisp works as well. In reverse Polish notation, the operand to an arithmetic operator are both placed before the operator. So 1 plus 2 becomes 1, 2 plus. Evaluation. Okay, well, this is an exercise, and I think we should be capable of doing it, but I don't know what I want to be. I don't know if I want to. Okay, so I think I'm going to leave it as an optional exercise to my viewers. And in the meantime, I'm going to go ahead and skip to the next chapter. Chapter 6, Parsing Expressions. This chapter marks the first, grammar which knows how to control even kings. Molière. This chapter marks the first major milestone of the book. Many of us have cobbled together a mishmash of regular expressions and substring operations to extract some sense out of a pile of text. The code was probably riddled with bugs and a beast to maintain. Writing a real parser, one with decent error handling, a coherent internal structure, and the ability to robustly chew through a sophisticated syntax, is considered a rare impressive skill. In this chapter, you will attain it. Side note, parse comes to English from the Old French parse, for part of speech. It means to take a text and map each word to the grammar of the language. We use it here in the same sense, except that our language is a little more modern than Old French. Another side note, like many rites of passage, you'll probably find it looks a little smaller, a little less daunting when it's behind you than when it loomed ahead. Back to the book. It's easier than you think, partially because we front-loaded a lot of the hard work in the last chapter. You already know your way around a formal grammar, you're familiar with syntax trees, and we have some Java classes to represent them. The only remaining piece is parsing, transmogrifying a sequence of tokens into one of those syntax trees. Some CS textbooks make a big deal out of parsers. In the 1960s, computer scientists, understandably tired of programming in assembly language, started designing more sophisticated human-friendly languages like Fortran and Algo. Alas, they weren't very machine-friendly from the primitive computers of the time. Side note, imagine how harrowing assembly programming on those old machines must have been that they considered Fortran to be an improvement. What does Fortran look like? Okay, what does Fortran look like? Give me a sample. Okay, well, I can see how this would be an improvement compared to... Okay, I can't understand any part of this. These pioneers designed languages that they honestly weren't even sure how to write compilers for, and then did groundbreaking work inventing parsing and compiling techniques that could handle these new, big languages on those old tiny machines. Classic compiler books read like phoning hagiographies of these heroes and their tools. Oxford Learners Dictionaries. Hagiography.
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 Hagiography. Hagiography.
Hagiography.
Hagiography. Hagiographies. Like phoning hagiographies. What about this one? Fawn.
Fawn. Fawn.
Fawn. To try to please somebody by praising them or paying them too much attention. He seemed unaware of the girl's fawning admiration.
Fawn.
Fawn. Classic compiler books read like phoning hagiographies. Like phoning hagiographies of these heroes and their tools. The cover of Compilers, Principles, Techniques, and Tools literally has a dragon labeled Complexity of Compiler Design being slain by a knight bearing a sword and shield branded LALR parser generator and syntax directed translation related on thick. A little self-congratulation is well deserved, but the truth is you don't need to know most of that stuff to bang out a high-quality parser for a modern machine. As always, I encourage you to broaden your education and take it in later, but this book omits the trophy case. 6.1 Ambiguity and the Parsing Game. In the last chapter, I said you can play a context-free grammar like a game in order to generate strings. Parsers play that game in reverse. Given a string, a series of tokens, we map those tokens to terminals in the grammar to figure out which rules could have generated that string. The could have part is interesting. It's entirely possible to create a grammar that is ambiguous, where different choices of productions can lead to the same string. When you're using the grammar to generate strings, that doesn't matter much. Once you have the string, who cares how you got to it? When parsing, ambiguity means the parser may misunderstand the user's code. As we parse, we aren't just determining if the string is valid logs code, we are also tracking which rules match which parts of it, so that we know what part of the language each token belongs to. Here's the logs expression grammar we put together in the last chapter. So the expression is, okay. This is a valid string in that grammar. But there are two ways we could have generated it. One way is starting at expression, pick binary. For the left-hand expression, pick number and use 6. For the operator, pick slash. For the right-hand expression, pick binary again. In that nested binary expression, pick 3 minus 1. Another is starting at expression, pick binary. For the left-hand expression, pick binary again. In that nested binary expression, pick 6/3. Back at the outer binary, for the operator, pick minus, and for the right-hand expression, pick number and use 1. Those produce the same strings, but not the same syntax trees. In other words, the grammar allows seeing the expression as 6/3 minus 1 or 6/3 minus 1. The binary rule lets operands nest any which way you want. That in turn affects the result of evaluating the parse tree. The way mathematicians have addressed this ambiguity since blackboards were first invented is by defining rules for precedence and associativity. Precedence determines which operator is evaluated first in an expression containing a mixture of different operators. Precedence rules tells us that we evaluate the slash before the minus in the above example. Operators with higher precedence are evaluated before operators with lower precedence. Equivalently, higher precedence operators are said to bind tighter. Side note, while not common these days, some languages specify that certain pairs of operators have no relative precedence. That makes it a syntax error to mix those operators in an expression without using explicit grouping. That means it's an error to use that operator more than once in a sequence. For example, pairs range operator isn't associative, so A until B is okay, but A through B through C is an error. Associativity determines which operator is evaluated first in a series of the same operator. When an operator is left associative, think left to right, operators on the left evaluate before those on the right. Since minus is left associative, this expression is equivalent to 5 minus 3 minus 1. Assignment, on the other hand, is right associative. This is equivalent to this. Without well-defined precedence and associativity, an expression that uses multiple operators is ambiguous. It can be parsed into different syntax trees, which could in turn evaluate to different results. We'll fix that in logs by applying the same precedence rules as C, going from lowest to highest. For equality, we get left associativity. For comparison, left associativity. For term, minus and plus we got left, and then factor and unary. Right now the grammar stuffs all expression types into a single expression rule. That same rule is used as a non-terminal for operands, which lets the grammar accept any kind of expression as a sub-expression, regardless of whether the precedence rules allow it. We fix that by stratifying the grammar. By the way, stratifying, I think it means defining layers, in case you're not an English native speaker. Stratification. Stratify.
Stratify.
Stratify. We fix that by stratifying the grammar. We define a separate rule for each precedence level. Side note, instead of baking precedence right into the grammar rules, some parser generators let you keep the same ambiguous but simple grammar, and then add in a little explicit operator precedence metadata on the side in order to disambiguate. Okay, so each rule here only matches expressions at its precedence level or higher. For example, unary matches a unary expression like negated, or a primary expression like 1, 2, 3, 4. And term can match 1 plus 2, but also this. The final primary rule covers the highest precedence forms, literals and parenthesized expressions. We just need to fill in the productions for each of those rules. We'll do the easy ones first. The top expression rule matches any expression at any precedence level. Since equality has the lowest precedence, if we match that, then it covers everything. Side note, we could eliminate expression and simply use equality in the other rules that contain expressions, but using expression makes those rules read a little better. Also, in later chapters, when we expand the grammar to include assignment and logical operators, we'll only need to change the production for expression instead of touching every rule that contains an expression. Over at the other end of the precedence table, a primary expression contains all the literals and grouping expressions. So the primary is a number or a string or a boolean or nil or a grouping expression. A unary expression starts with a unary operator followed by the operand. Since unary operators can nest, bang bang true is a valid if weird expression. The operand can itself be a unary operator. A recursive rule handles that nicely. But this rule has a problem. It never terminates. Remember, each rule needs to match expressions at that precedence level or higher. So we also need to let this match a primary expression. That works. The remaining rules are all binary operators. We'll start with the rule for multiplication and division. So a factor could be a factor slash or times unary or a unary. The rule recurses to match the left operand. That enables the rule to match a series of multiplication and division expressions like this. Putting the recursive production on the left side and unary on the right makes the rule left associative and unambiguous. Side note, in principle it doesn't matter whether you treat multiplication as left or right associative. You get the same result either way. Alas, in the real world with limited precision, Roundoff and overflow mean that associativity can affect the result of a sequence of multiplications. In languages like LOX that use IEEE 754 double precision floating point numbers, the first evaluates to 0.006, while the second yields 0.006 with a lot of zeros and a 1 at the end. Sometimes that tiny difference matters. This is a good place to learn more. Oh my, why is it a link to Oracle? Okay, maybe we could actually read this document during another video. I'll see if this is interesting, and if it is, maybe I'll read it. If you would like to listen to it, let me know in the comments below. Back to the text. All of this is correct, but the fact that the first symbol in the body of the rule is the same as the head of the rule means that this production is left recursive. Some parsing techniques, including the one we're going to use, have trouble with left recursion. Recursion elsewhere, like we have in unary and the indirect recursion for grouping in primary, are not a problem. There are many grammars you can define that match the same language. The choice for how to model a particular language is partially a matter of taste and partially a pragmatic one. This rule is correct but not optimal for how we intend to parse it. Instead of a left recursive rule, we'll use a different one. We define a factor expression as a flat sequence of multiplications and divisions. This matches the same syntax as the previous rule, but better mirrors the code we write to parse logs. We use the same structure for all of the other binary operator precedence levels, giving us this complete expression grammar. Expression equals equality, and then equality equals comparison. Okay. And then comparison is one of these, and then a term factor unary primary, and the primary is okay. Yeah, well, this is actually very clever if you look at it like this. This grammar is more complex than the one we had before, but in return we have eliminated the previous one's ambiguity. It's just what we need to make a parser. (6.2) Recursive descent parsing. There is a whole pack of parsing techniques whose names are mostly combinations of L and R. LLK, LR1, LALR, along with more exotic beasts like parser combinations, early parsers, the shunting yard algorithm, and Packrat parsing. For our first interpreter, one technique is more than sufficient: recursive descent. Recursive descent is the simplest way to build a parser and doesn't require using complex parser generators tools like Yak, Bison, or Antler. All you need is straightforward, handwritten code. Don't be fooled by its simplicity though. Recursive descent parsers are fast, robust, and can support sophisticated error handling. In fact, GCC V8, the JavaScript VM in Chrome, Roslyn, the C# compiler written in C#, and many other heavyweight production language implementations use recursive descent. It rocks. Recursive descent is considered a top-down parser because it starts from the top or outermost grammar rule, here expression, and works its way down into the nested sub-expressions before finally reaching the leaves of the syntax tree. This is in contrast with bottom-up parsers like LR that start with primary expressions and compose them into larger and larger chunks of syntax. It's called recursive descent because it walks down the grammar. Confusingly, we also use direction metaphorically when talking about high and low precedence, but the orientation is reversed. In a top-down parser, you reach the lowest precedence of expressions first, because they may in turn contain sub-expressions of higher precedence. Yeah, whatever. A recursive descent parser is a literal translation of the grammar's rules straight into imperative code. Each rule becomes a function. The body of the rule translates to code roughly like terminal, call to match and consume a token, non-terminal, call to that rules function. Okay. Yeah, okay, well. The descent is described as recursive because when a grammar rule refers to itself, directly or indirectly, that translates to a recursive function call. Okay, back to the side note. CS people really need to get together and straighten out their metaphors. Don't even get me started on which direction a stack grows, or why trees have their roots on top. 61, parser class. Okay, I'm not sure if we can start with this one, because we're almost at the 1 hour mark. So I guess we're going to write the parser in the next video. And in the meantime, if you liked this video, please consider supporting this channel by hitting the like button or maybe even subscribing to the channel. And if you have any questions, you can leave them in the comments below. As always, the code for this video will be available as a link in the description below. I hope you learned something and see you in the next video. Oh, and by the way, the name is Karol Moros, and you've been watching Make Programming Fun Again. Bye!